there's quite a lot to unpack in the title here. Probably a few terms that might be new to you. But I'm going to start with the plugin side of things. Then I'm kind of going to introduce ML for audio developers who might not necessarily be experts in that field. Before moving on to DDSP and then kind of talking a bit about where we go from there. Before I start, I wanted to thank, in particular, my colleague Hanoi, who helped me a great deal put these slides together. So thanks to him. All right, so plugin side of things. I hope some people in this room are aware of Morph. We released it earlier this year. It is a timbre transferring resynthesizer. You can use it as a creative effect, or you can play with it with a MIDI keyboard if you like. It analyzes the pitch of some incoming audio and resynthesizes a performance of an instrument that it was trained on with audio. We built it at TikTok. You're probably familiar with TikTok. It's an entertainment platform, specifically for short-form mobile video. And while our mission is to inspire creativity and bring joy across the company, that creativity and joy can obviously take many forms. And for our team, that's audio, and I'm looking forward to sharing that with you. If you want to try Morph yourself, it's free. You just need to sign up with an email address online. That's it. Download it, give it a try. It's good fun. Okay, I think the best way to explain what it does is just to see it in action. So here's a little demo video that my colleagues put together. We are not just trying to get professional music producers to be creative in their home studios as well. We're trying to encourage people who are not musicians to be musically creative as well, and to share that joy with the world as much as we can. So the technology behind Morph, we integrated into TikTok as a voice effect, and that runs completely on mobile, on device. And you can see how that... Boo. All right. And the nice thing about this is the synthesis of the trumpet in the first example, the swana, which is a double reed horn from China, and the flute here all use the same algorithm. It's just different parameters that have been learned from audio. We got some nice press for it, and another thing that we're really excited about is the transcultural possibilities of this technology. The winner of the AI Song Contest this year used it in order to kind of make use of Thai tuning systems and Southeast Asian melodies in Western bass music, and we think that cross-pollination is super, super exciting. It's not just the work of one or two people, a whole wonderful team of very, very talented engineers, scientists, and music producers put this together. So this talk is really from everyone. So thanks to them. You might be wondering why TikTok are here. We do have an audio team. We cover quite a lot of stuff. Our team is called SAMI, stands for Speech, Audio, and Music Intelligence. And we cover all the usual suspects in the audio world. where we sit and where this work came from was our music intelligence section. We cover stuff from music understanding all the way through to real-time synthesis. So that was us. Okay, so what's on the agenda for today? The main bulk of the talk is in the first two sections. I'm going to give a quick guide to differentiable DSP, what it means, how it works, then do a bit of a deep dive into our model and how we got things working and what's going on under the hood. I'll be able to give a short note on some engineering challenges that we faced and how we solved those, and then a very quick outlook on what we'd like to do next. Okay. I think I'm going to explain this best with a worked example, and let's go right back to basics with the very simplest possible DSP unit we can think of, and that's just a gain. Well, perhaps maybe it's a bit more complicated than that when you start really diving deep, but let's just treat it as a simple fader. Now, this explanation is aimed at those of you in the audience who are not experts in machine learning. I appreciate there are probably some people in the audience who are experts in machine learning, and a little apology to you, this will probably be quite dull. But the aim of this section is for audio developers who are not experts in ML. I'm going to try to build an intuition for what DDSP is and how you might be able to make decisions around that technology in your own work. Okay, we have a fader. A simple fader, but this problem's a little bit different in that we don't know where the fader is positioned. It could be here or it could be here. But we want to capture that somehow. We might have some sort of physical model, well, it might not be physical, it might be informed by other information, but we have a model that we think is general enough to capture the system in some way. We don't know M because we don't know where the fader is, this gain. Our model gives us a prediction for the output, y hat. Given some input x, we can apply a gain with our parameter m to get a prediction of the output. But we don't know what m is because we don't know where the fader is. But with a little bit of help from a data set, in this case, we might have a list of input and output pairs. We can find out a little bit more. I'm sure those of you in the room who are humans can see what M is. As a show of hands, who can see what M is? Thank you very much. Anybody? 2, yes, absolutely. It is definitely 2, and you are a smart human, and you can see that straight away. But what if you're not a smart human? What if you are a machine that only follows instructions? How do we find m is equal to 2? That's our task. The task is find our parameter that best matches the data. Okay, so we're going to start with just some guess. Any guess. M is equal to 3. For each of our dataset inputs, x, we can use our model, we can invoke our model to get a prediction for what we think the output would be. We can also compare that to what the true values are in our data set. And if we're a little bit clever, we can try to start to quantify how well we've done. If we kind of define some measure of how badly we match the data, then maybe we can add them all up and get a total badness. Machine learning engineers and researchers will call this a loss. And you can see we have a total of 6 here. We're 2 away here, 1 away here, 1 away here, 2 away here. And adding them all up, we get 6. We can begin to start plotting how well we're doing for each parameter that we're guessing. And we can repeat the process. We can do it for m equal to 4. Do exactly the same thing, quantify how well we did, calculate our loss, and oh dear, we found that we've done even worse this time. Things aren't going well. Right. Ooh. That skipped a lot. Oh, that's sad. Never mind. Okay, our machine. Back to the story. Let's try 1. We found we've done just as badly as 3, and if we try m is equal to 0, then you see where this is going. We're not doing so well. One way that we could maybe find m that would be very bad, you got a little hint at it when you peeked ahead at the slides, would be to just try all of them. We could search the entire space, and then we'd find out, that our loss, how badly we did, is minimized when our parameter matches the data. But what if we don't just have m? What if we have a million m's that we need to find? What if we have a billion m's? Even way before we get to a million, searching that entire parameter space is going to rapidly become completely intractable for modern CPUs. So we need some way to find it quicker. And here's how we're going to try to do it. So we're starting again with our initial guess. And if you remember from the last slide, what we ended up with was this sort of curve here, this surface-like structure. And if we can quantify that, if we know which way is up and which way is down, we can make our guess move towards a better guess. We can improve our estimate. So, mathematicians will describe this slope as a gradient. And if you know the gradient, you can step down the hill. You can step down the gradient. So we can make a better guess, and again, and repeat the process until we've reached our target faster. Machine learning scientists and engineers will describe this process as training, and they're learning M. And so that's where that sort of language comes from if you're new to this space. All right. Problem is, us as smart humans, we can look at that curve and we can say, okay, that way's down. But if we have a complex system, how do we actually tell the machine which way is down the hill? Well, just a little recap. What we did was we had given some model parameters and an ability to invoke our model. We're going to evaluate how well we did. That's what we did. We evaluated our loss. And we can think of this as in the forwards direction. And this is a forward step. What we actually want is kind of to go the other way around. Given how well our model matches the data and some knowledge of these model internals, how do we actually best change our parameter in order to better fit the data? How do we locate? How do we get closer to the fader position that we're after? We're calling this a backward step. Okay, so this is the gradient we seek in the vicinity of our point. And the important thing is when we're exploring this space, what information we don't have yet is the gradient everywhere. Just like we don't know the surface everywhere until we actually calculate it, we don't know the gradient everywhere. So what we're going to try to do is evaluate it in the vicinity of our guess. So we're seeking the loss gradient as a function of our parameter. Unfortunately, we don't have an expression for that. Maybe in our restricted case, you could get an expression for that, but what happens if you have lots and lots of different architectures, lots of different processes? You're not necessarily going to have an expression for the loss as a function of your parameters directly. But what you do have is an expression for your loss as a function of the output of your model predictions. The output of your model predictions is a function of your parameters. So if you've studied some mathematics, you'll know that we can use a chain rule to get the quantity that we're after. But you can only do that if the loss expression and your prediction are differentiable. If we know which way is down from the vicinity of the point, we can step in a better direction and get to where we want to go. For the multivariate case, this is what the chain rule looks like. We're going to step through the maths in fairly good time. Don't worry if you don't follow all of this, but the derivative of our model with respect to x, which is fixed, with respect to m, given that x is fixed, is of course just x. And eventually you get down to this expression here. There's a little bit of branching that comes in from the modulus operation here. But this is what we have. And just like we were before when we had our table and we could calculate the loss, we can do exactly the same thing. And for each point, calculate the contribution to the gradient. When we add them all up, we can get a total. And this gives us a measure of the slope in terms of an actual number. So 6 is positive. That means if we increase m, our parameter, it means the loss is going to go up. So in order to get the loss to go down, we want to decrease m. If we'd done that for m is equal to 1, we would have been told the opposite. We would have found, OK, our gradient's negative. That means if we increase m, we're going to go downhill. And that's good news for us. So we step downhill, and we can get to m is equal to 2. So this process of calculating gradients and changing our parameters of our model, we know as backpropagation. So we've gone from a loss through our model back to the parameters. This extends, of course, to more parameters. If you have 2, you can sort of start to think about this like contours on a map and trying to find the deepest valley. Mathematicians will know this process as gradient descent. It also extends to more operations. You might not just have one process happening in your model. You might have some hidden ones, h. The same principle applies. Eventually, you'll get into this whole rich world of very large and complicated topologies that are extremely powerful and can learn millions and millions of parameters to do all sorts of very exciting things. But the take-home message about this is the fundamental principle is exactly the same. Everything that's going on here is all about somehow being clever and quantifying how badly you did when trying to match the data and backpropagating the information into the model in order to change your parameters to try to better match the data. And all kind of common machine learning frameworks out there handle all of that process for you. So your task is to just define these topologies and your loss functions, and more to it than that, of course, but that's the basic principle. All right. The thing, of course, that relies on in order to work is that all functions in the network are differentiable. So what does that mean? Differentiable functions versus not differentiable. I'm not a mathematician, so I apologize in advance to mathematicians in the room. Perhaps that might make you cringe a little bit, but differentiable functions are continuous. They don't have vertical tangent lines, and they don't have breaks in them, they don't have angles in them, and they don't have cusps. In practice, this is most functions used in common mathematical practice. Things that are not differentiable are discontinuities and discrete choices. So if you have a function that does something along these lines, are you going to do one thing if a choice is one particular choice and another if it's another? You're going to have to think about reframing your system in terms of differentiable functions if you want to make use of this sort of technology. All right, so what about the functions we use in music DSP? Which ones of those are differentiable? Well, it's mostly good news. So we've just seen that gain is differentiable. If gain is differentiable, then pan's differentiable, right? Summation's differentiable. The sum of the derivatives is the derivative of the sum. The linearity of the derivative. And with those three things, we've already got ourselves a mixer. Sinusoids are differentiable. If sinusoids are differentiable and those things are differentiable, then additive synthesis is also differentiable. If additive synthesis is differentiable, then wavetable oscillators are differentiable. Convolution is differentiable. And if convolution is differentiable, then FIR filters are differentiable. If convolution is differentiable, then delay is also differentiable. Why is that? You can frame delay as convolving with a delayed impulse. IIR filters are differentiable. State space filters are differentiable. That was some work done by some people in the room. And wave shapers are also differentiable if you choose the right ones. So all of these things are differentiable, which already gives us quite a lot of powerful things that we can start to use. Okay. Let's compare the two approaches a little bit. If you're writing DSP, you tend, this is obviously a big generalization, you tend to carefully design your algorithms. ML, you can throw lots of resources at it. Big models, lots of data. These DSP algorithms tend to be very, very interpretable. Now, this is going to be an important word that I'm going to talk about a lot. And what I mean here is that we can understand what's going on in there as humans. Like, we know what a filter frequency means. We can understand that. We can change it, and we can make expectations about how the sound is going to change when it comes out the other side. But the thing about the DSP approach is often these are very carefully designed, and they work very, very well for some use cases, but as soon as you want to use your algorithm to do something different, it's not going to work quite so well. They're smaller and easier to run in real time, generally. With machine learning and these very, very large networks, the same topology and the same algorithm can do lots and lots of different things depending on what data you train it on. And that makes them very generic, but they also tend to be black boxes. We can't really reach into the intermediate representations going on in there and play around with them and make sort of human-level inferences about what's going to happen. Because they're so large and use so many resources, they also tend to be quite tricky to run in real time, although people are solving those problems. So these red bits, can we get the best of both worlds? That's the aim of the game. All right. With pure DSP, we have some sort of DSP algorithm that, with inputs, we do some processing, we get our output. The algorithm's interpretable. The processing is fast, but the output is specific. Let's compare that again with pure ML. We have a large ML model, make some predictions based on our input, and we get our output. If we can backpropagate our gradients, we can train this system end-to-end. So that's a giant advantage we have there. We don't need to design a new thing for each individual new use case. Big black box, there's the ML model. Predictions tend to be slow, but we do like the genericness of the output. Right, let's try to combine these. We have our ML model, make some predictions. If we can stick something on the end of it that is a differentiable DSP algorithm, we can do our processing and get our output. Because the DSP algorithm is differentiable, we can still train this end-to-end on data. The differentiable DSP algorithm is just as interpretable as the one on the top left. We can reach into that and we can play around with it. We can be creative with it as musicians. You'll also notice that, I mean, let's have a think about that differentiable DSP algorithm. What if it's a fader? What if it's just a fader? That imposes a really, really strong guardrail on what the output can be. You know, this machine learning model, the only thing that it can control here is the position of that fader. It doesn't have to guess all of the samples, the output samples for all of the input samples. It just needs to guess the position of a fader. And that means that the output is going to probably sound not that crazy all of the time. Because it's an easier task, generally, the machine learning model can be much smaller. It doesn't need to be as big, which means that it can make predictions much faster. Our DSP algorithm is just as fast, and our output is generic. And this is the kind of the ideal situation that we're looking for in this particular case. So we've kind of reached this understanding here that DDSP is classical signal processing combined with modern machine learning. But we get this extra bonus, which is really cool, especially for music-making tools, in that the interpretability of the differentiable algorithm allows us to offer an actual creative interface to AI. And we're really excited about that. All right, 1 second. That was a cool sound. All right. So our particular model, I'm going to describe a little bit about what it looks like under the hood, how it works. There's 2 models, really. One is in TikTok, which is going to be kind of in this cyan color. And that's been extended. We've added extra things into it in the plugin. And you'll be able to identify those with the lilac color as well. And this is what it looks like. I'm not sure if you can see that in the room very well. Yes, I think so. OK. Thank you for dimming the lights. We have our input, X. This is just audio. Our audio goes through a pitch detector. Xavier, thank you for the wonderful talk earlier. It was very, very relevant for this. Once it comes out the pitch detector, we're no longer working with audio. We've got a MIDI pitch signal that we're working with. All right. In Morph, we added these extra creative pitch controls, and these then feed down into the brains of the operation, and that's what we call a decoder network. Amplitude detection happens as well on a separate branch, and in Morph, again, we added these extra creative controls to play with the amplitude that goes into the model. The model does its thing and predicts some control parameters for our synthesis algorithm. So this is the ML bit, and this is the DDSP bit. Likewise, the model predicts some noise magnitudes. That goes into a filtered noise synthesizer. And we're back in the audio domain. Just like the pitch controls and the amplitude controls, we added extra creative possibilities onto the end before we sum our audio signals and we get the output audio. And that's the high level. And so then the next section of the talk, I'm going to kind of step through each one of these items and just talk a little bit about what their job is and how they work. So let's start with our pitch detector. So the cool thing about this is it doesn't need to match what you used in training. It doesn't matter. That ML bit that was in the middle, it doesn't care what pitch detector you use. It has no knowledge of that. All it knows about is that it gets a pitch as an input. So you have a lot of options. There's a new one out called CREP. Swipe, which is a sawtooth waveform-inspired pitch estimator. Yin, P-Yin, probably many more. Or you can roll your own. There's lots and lots of options. Any will work. And because any of those will work, maybe you might want to control it directly. Maybe you might want to use a MIDI keyboard to provide that pitch information. For some instruments, using a MIDI keyboard is actually easier to control the pitch. Something like a saxophone or, I don't know, a piano or something starts to sound very unnatural if you have smooth pitch glides that you get with a voice. Maybe that's desirable, though. This allows you to be creative with it. All right, once we have our pitch signal in MIDI space, we can do whatever we want with it. We can transpose it, we can pitch it up, we can add some vibrato with an LFO, and that's what we did. You can play around with that in the plugin, and this allows you to push this kind of acoustic instrument way beyond what it could originally do with real physics. All right, with amplitude detection, again, you have a lot of options. You might want to use some A-weighted RMS detection, plain RMS detection. You can use a low-pass filter, depending on your needs, or some sort of branching ballistics filter, spectral methods, whatever. You can roll your own, do what you want. Doesn't matter. Any will work. All you need is an amplitude signal, or a MIDI keyboard with an envelope generator. And this is where things kind of get quite fun, because again, like the pitch controls, you can play around with the amplitude as a creative control in your plugin. You can apply input gain, you can apply some compression or expansion, transient shaping. And the nice thing about this is we're not processing audio here. We're processing input signals to the model. So in training, what the model has learned is it sees, okay, when there's a high amplitude, I'm getting lots of harmonics out of my flute. Right? When it's a low amplitude, I'm not getting so many. So if you go in and you kind of play with this input gain here as a creative control, if you increase the gain, you're not just changing the level of the audio coming out. You can actually make that flute overblow. And you can play with that as a creative performance control. Okay. The decoder network is our pure ML part. This is the brains of the operation. And its purpose is, as I said, to take pitch and amplitude inputs and generate some harmonic amplitudes and some noise magnitudes. We'll see how these are used later. But the key info about this is there's a fair amount of information to predict here. And so we need to run inference frequency much slower than at audio sample rate. The network is stateful, and that's how it understands the time dependency of timbre. There are open source papers that use a very, very similar model, and there are open source implementations available as well, so do check those out if you want to learn more. Okay. Once we have our harmonic amplitudes, A, and if we have our fundamental frequency from our pitch detector earlier, we can feed this into an additive synthesizer. This gives us a purely harmonic audio output, very pure tones. Wavetable synthesis is just as general as additive synthesis if your harmonics are multiples of each other. So that's how we implemented it. We did the additive synthesis with wavetables. The noise synthesizer works in a very, very similar way. We just predict these noise magnitudes over time. These go into this time-varying noise-shaping filter, and that filter just processes some white noise that is being generated all the time. So when these noise magnitudes are very low, this will basically just be a flat line here, and you won't hear any noise coming out whatsoever. But when these noise magnitudes are higher, you start to get really nice and interesting breath contours for wind instruments, or bow contours for violins and other stringed instruments. All right, okay, so I wanted to kind of take a little moment here just to mention again that just like earlier, and we had the single fader differentiable DSP algorithm, that imposes some pretty fiercely strong guardrails on the model. These DDSP units also impose some strong guardrails on the model. The only thing that can come out here are harmonics that are pure, mixed with some filtered noise. So maybe, is there somebody in the audience who might be able to tell me what kinds of instruments this might be well suited to? Anyone? What about instruments that it would be, oh yes, please. Monophonic, yes. Absolutely, yes. Yeah. Any other instruments it might be well suited to? What about not well suited to? Anybody got any ideas about where this model might start to fail?
In Trevelyan xylophone. Because in its harmonic profile, it only has the second and tenth harmonic. Something weird like that.
Okay, interesting. Sorry? Absolutely, yeah. Drums, definitely. Yeah. All right, so this model is very well suited to instruments whose physics exhibit natural harmonic motion. Instruments that have kind of one dimension that dominates the motion. We have instruments that are excited by noisy signals, like a flute, that's excited by breaths. Violins are excited by dragging a very rough bow across a string. That's another noisy signal. Because the inference runs at a much lower rate than audio sample rate, just like drums, we can't really deal with transients that are very strong so well. That doesn't work so well in this particular model. And we also need the fundamental frequency to change relatively slowly. So that means things like blown pipes, bowed strings, and animal vocalizations. You'll find a cat model in TikTok if you want to play around with that. It's very poorly suited to instruments with physics that exhibit strong non-harmonic motion. It's unclear whether they have unclear or detuned frequencies. So something like a sitar, for example, will be very difficult for this pure harmonic model to pick up and replicate well. And yeah, on the drums theme, if it's excited by transients or they are inherently transient, we're going to struggle. And if there is no easily detectable fundamental frequency, we're also going to have a hard time. So these tend to be things like drums, gongs, bells, and detuned strings. All right. And then finally, the last creative controls that we offered is just a simple crossfader between the output of the noise synthesizer and the output of the harmonic synthesizer. And that was just so we could offer our pro music users to be able to take different signatures of these instruments and mix them with other sound sources that they might find fun. So we generally find that through training, the noise synthesizer tends to reproduce the sounds of breaths of a flute. And if you isolate that, you can then layer it with other things. And that's a really fun thing to do. You might have other noise sources of your own that you're interested in using, but maybe you might like the harmonic signature of a flute. That's also possible if you just set the crossfader over to full harmonic. And that's it. And I think let's see what it can do. Actually, no, I think we're going to run out of time, so I'm going to skip this. You can find this. You can find that video on Morph website. It's morph.io. All right. I don't have long, so I'm going to do a short engineering note on how we built it and what challenges we faced. So I think there are people in the room who have probably faced the same challenges, and this will be a familiar site, but you have many rates to deal with. You have your training sample rate, your training model rate, training buffer size. These are all fixed, but as soon as you want to get this into a DAW running in real time, you're gonna need to solve this particular problem. Real-time machine learning inference as well. That's a big topic, but be aware that popular machine learning frameworks don't necessarily offer a real-time safe API. They don't necessarily offer real-time safe implementations under the hood, so that's going to make it hard for you to run this on your audio thread. If you don't want to run it on your audio thread, you'll obviously incur that extra latency, which may or may not be acceptable for your particular use case, depending on what other units you've used in your system. Open source solutions to this problem are available. Is Jatin in the room? No, he's not. Jatin Chowdhury has released RT Neural, and he's building a library that you can use to run real-time inference on your CPU, on the audio thread, in safety. And then the other tricky bit we found was because we had so many choices about which real-time units we wanted to use, combining those, they obviously don't match the training conditions exactly. And that can lead to a bit of a loss of realism, which might be desirable, but if it's not desirable, you'll need to do some massaging of those signals. All right. I wanted to make a little note on our testing approach. We're very proud of our test-driven development process, and it's very hard to do in audio, but we think it's extremely worthwhile. And just this is how we do it. This is how we approach it. This is our testing philosophy. I think this would be a fun talk on its own, but I don't have time today. But for low-level algorithms, we unit test observables only. We just check inputs and against expected outputs. But for higher-level algorithms like this one, you'll recognize this picture. We use a lot of dependency injection and mocking, and that's so we can make meaningful assertions on all these bits of connecting code. So by replacing the real bits of the system with mocks, we can make meaningful assertions about what has been called on those and the data that went in and out. At our user interface level, we only test behavioral logic, again with dependency injection and mocking. We just trust that our UI framework gives us the right pixels. We don't try to assert anything on those pixels. For thread safety, we found by being a bit creative with your unit tests and designing very pathological use cases, you can capture most problems in an automated test suite and get failing tests for when you don't actually do things safely. Likewise, with real-time safety, by being a bit creative, you can also capture a bunch of problems. But one thing that we found, which is really fun, is LLDB's Python API. And if you're happy to test a debug build, you can script this and get failing tests when real-time unsafe things happen, like a call to system calls and stuff like that. And that can all go into your CI pipelines. All right. OK. I think I'm reaching the end now. Just a short note on where we want this technology to go. Our mission is obviously to inspire creativity, not to replace it. We want to build lots more tools that will bring joy to the world. We want to see more open box models, things that are interpretable, where you can reach in and play around and be creative with the signals internally. And it's really important that these tools are also breakable. One of the controls we offered was this input gain, and you can push it way beyond or way below what the model's seen in training. And then it does some really weird things because it hasn't seen any signals like that before, so it just does its best guess. But we think capturing that is super important because so many amazing developments in the world of music have come from misuses of technology and breaking things deliberately. All right, that's everything. Thank you very much. We're hiring. Come and find us at our booth. And thanks again for your attention.